So today topic is second part of electromagnetic induction. So as we know, the origin of induced EMF, origin of induced EMF, first is a motional EMF and second is a induced electric field. Okay, so first I am going to discuss about the motional EMF. Okay, so the motional EMF. So now you can see the given informed magnetic field and direction of magnetic field is a into the plane. Okay, second thing, you have one conductor length L and moving with velocity v. Okay, length is a given L. Okay, and the magnetic field into the plane. So the first condition for the motional EMF is B, L and V all perpendicular to each other. Okay. So when conductor, because this is the conductor, when conductor is moving in magnetic field, the force will act. So if force on charge, suppose I am taking charge Q, so the magnetic force, this will be Q into V cross B. Okay. So in the conductor, as we know, there is a positive charge as well as negative charge. So positive charge, so force on the positive charge in this direction, and the force in negative charge will be in this direction. So the positive charge will accumulate on the this end and negative charge will accumulate in the upper end. So in between, now you can see in the conductor, here you have positive charge, here you have negative charge. So now you can see in between there will be electric field will produce, and there will be another force, electric force will come, that will be charge accumulated here Q1 into electric field between the positive and negative. So keep charge will accumulating till when these two forces, magnetic force and electric force, this will be equal. That time it will stop the charge accumulating. So you can write Q into E, that equal to Q into VB, because V and B is a perpendicular to each other. So now here you can write electric field equal to velocity into B. Now we know the relation between electric field and potential difference. So you can write dV by dr, or you can write here for the uniform electric field V by L, because L is given the length of conductor. So the potential difference will be E into L. Okay, and you can see in the last E equal to V into B. So the potential difference will be VBL. So you can write BLV. So the induced EMF is BL and V is a velocity. And the important point is you can see velocity was in this direction, magnetic field was into the plane, and length in this direction. That is the reason we have induced EMF. And then current flow in this BLV by R. You can draw the equivalent circuit like this. If you have positive and this is a negative, and then you can connect with resistance. This is the your induced EMF. This is the R. Okay, why I am taking only the perpendicular direction? Because if you take here, if you have a conductor like this, okay, and then velocity moving in this direction, L also in this direction. Okay, so the force will act in this direction or in this direction, magnetic force. So where charge will accumulate. So that is the reason I am only taking, so B, L, V must be perpendicular to each other. Then you have motional EMF equal to B, L, V. Take example, suppose that one string is a following. Suppose that one semicircular ABC is a following down with a given magnetic field is a out of the plane, okay, with radius a small r, okay, with constant velocity is a like V. What is the motional EMF? So the motional EMF, see here, because if you take any a small element like it dl, okay, so dl has two components, one component in this direction and other component in this direction. So only this component is perpendicular to the magnetic field as well as velocity. So you have to take only horizontal component like this, and projection of this semicircular along this direction will be 2r. So directly you can write B, for L you can write here 2r and V. So 2BRV will be your answer. Thank you. This is a question I am going to take related to the motional EMF. So this is the coil, closed loop, and this is the conductor PQ is moving with constant speed V. Okay, this length is given of conductor is L. Okay, resistance of the closed loop is given R. Find the induced EMF and induced current. So first you have to think about, because velocity is a conductor is moving with constant velocity, it means flux is going to increase. Okay, so because magnetic field is increased, more magnetic lines will come in this closed loop. So the flux, as you know, that is AB cos theta. Okay, what is the area? This length is L, and suppose that any time you have, this is the x distance. So you can write area equal to L into x multiplied by B. B is a magnetic field. So B is into the paper or into the plane, and area will be outward. So the angle will be cos pi. So you can write flux equal to minus B L x. Okay, you know the induced current is equal to d change of flux with respect to time. So you can write B L dx by dt, because here given B is a uniform, B is a given and this is the uniform, so it will be constant. So now you can write here B L V. So the induced EMF will be B L V. What about the current? Okay, so you can write current equal to B L V divided by R. But the important point, what is your direction? So the induced current will try to oppose the change. What is the change here? Because magnetic field is increasing, flux is increasing. So due to induced current in this loop, try to oppose the initial. So what is initial direction of magnetic field? This is into the plane. So in P and Q, so direction of current will be P to Q. So you can see inside this will be magnetic field due to induced current will be outward. So that this is going to oppose the initial direction of magnetic field. You can also draw, so the direction of current, you can write here direction of current in the loop, that is a P to Q. You can also draw the equivalent circle. So here you can make plus and this is the minus, okay, and you can connect with the some external resistance. This is the you have, this is a plus and minus, this is a P and that is a Q. So current will flow like this. Okay, thank you. So this is the next question. So you can see the coplanar loop is a flash in a perpendicular magnetic field, so in this figure, and magnitude of magnetic field is a given case 1 is a constant with respect to time, second case is a decreasing with respect to time, third is a increasing with respect to time. And I1 and I2 are the current in the segment PQ and RS. Then find the direction of I1, I2. Okay. So now go for the case 1. Case 1 where magnitude of magnetic field is a constant. So the constant, it means flux will be also constant. So now you have flux is a constant, it means induced EMF will be 0, there is no current in the segment. Okay. Case 2. So now you can see the magnitude B is a decreasing. So B is a decreasing, it means flux will decrease. Okay. And it's a very important point, you have to see the closed section. So which one is a closed? So this is the closed section. It's a very important to see here. This part is a closed. You have to think about this. Okay. So now flux is decreasing. So then you have induced current. This will be the d phi by dt. But what is the direction? So of course induced current will try to support the initial, will support the initial direction of magnetic field. Okay. So now you can see here. Okay, sorry. So you have to take one point here, that to find the magnetic field, because inside the closed loop you have to see about the direction of magnetic field. Okay. So now we have two segments P and Q, this one, another is given R2S. Okay. In R2S, think about, this is the point you have. So if current, where you need magnetic field, because induced current should support the initial. So what is initial direction of magnetic field? Is into the plane. So if you have R2S, then it will be outward. So S to R. Okay. Then you can see the magnetic field will be inside due to this S to R current. Okay. Then P to Q, you have to think about inside. So P to Q, if you have a current like this, then magnetic field will be inside. And you can see on the right hand side, you know that current in the direction of thumb, and then forefinger will give the direction of magnetic field. But you have to see here only inside the coil. Okay. So the second answer is a P to Q will be I1, and S to R will be I2. Now think about the case 3. So case 3 is a, because magnetic field is increasing. So magnetic field will increase, then flux will also increase. So the induced current will try to balance the initial. So try to reduce the initial magnetic field. So what is initial magnetic field? Into the plane. So so now here will be in this way R to S. So now we check, this is the point inside the closed loop, then magnetic field will be outward. And the P, if you have to take Q to P, so just put the thumb in the direction of Q to P, the forefinger will give you the upward direction, out of the plane. So now case 3, you can write I1, that will be the Q to P, and I2, that will be the R to S. So first point is a very important, you have to think about closed. Which one is a closed section? This is open, so there is no magnetic flux in this. So first criteria, we must have some closed loop, and closed loop is only this part. Okay. And the first case was the magnetic field was not changing, it means the flux is a constant. Then second part, flux is a decreasing, because magnetic field is decreasing. So the induced current will try to increase the magnetic field. Okay. And you know the direction of magnetic field, initial direction of magnetic field into the plane. So due to this, inside the coil, due to this current I1 and I2 must be inside the plane. So that is the reason you have here P to Q and S to R. So that is, if you have I here, then this side will be magnetic field will be outward, and this side magnetic field will be inside. You have to apply this formula. Okay, thank you.